So oxygen into the blood. So we have to get our oxygen from the lung tissue. It's on the assumption we're breathing all right and we haven't got emphysema and we're doing plenty of exercise. We have to get it across the capillary beds here, the alveolar. And these are very thin tissues. They're elastic tissues and collagen. So these are the two extracellular matrix substances which make up the alveolar. So the alveolar is an elastic tissue. As we breathe in, we widen our chest with the AP and lateral dimensions here, and we suck air in, and the air coming in is like in a balloon, so we stretch. And then when we breathe out, we don't have to do anything, we just let go, and it goes like a balloon back. So the alveolar itself are rich in collagen and elastin. So to test collagen and elastin, you know the familiar twang test on the wrist, on the back of the hand. So when we pull the skin here, because the same collagens that are in the skin are in the lung tissue itself. So the stretch test here, you pull it and test the strong indicator muscle. And if the muscle goes weak, this is an indication there's a collagen problem. And then if you pull it and let it go twang, and they go weak, then this is an elastin or recoil. So collagen gives us the shape to the tissue and holds us together. So it gives the shape. That is the outline of the organs and the tissues. The elastin gives the elasticity, the ability to bring it back. So elastic tissues are primarily the lung. So if you think about it, the lung is a very elastic tissue. Because if you lose the elasticity, then you can't get the breath in and out properly, and that's what emphysema is. Okay? So you can do the same thing in the intestine. The intestine is a very elastic tissue. You think of the stomach, how big it can get when it has a full meal, or 10 pints of beer. And then how small it can get first thing in the morning, and all the way through. Sometimes on examinations, on x-rays, you see enormous pockets of wind, and the intestine will give pain if it's distended or if it goes into spasm. So it's an elastic tissue. So if you find a problem here, you tend to find it's in all the elastic tissues in the body, not just on the skin. So you can test collagen and elastin. If a person has breathing problems, it might be wise just to do the twang test and to see how their collagen and elastin is, and look at the nutrients involved with that. So the membranes of the lungs and there are made of phospholipids. These are oils attached to various phosphate groups, and the popular or common ones are phosphatidylcholine, which is the predominant one in the body, phosphatidylethanolamine, phosphatidylserine, sphingosine, which together account for more than half of the lipids in the membranes. So here we see basically what they are is like a tadpole with two tails, and the tails face inwards to stop water from passing through. So they're partially permeable. So the phospholipids in the red cell are asymmetrically distributed between the two halves. The outer leaflet consists mainly of phosphatidylcholine, whereas the phosphatidylethanolamine and serine are on the inner parts. We also have phosphatidylinositol in the membranes there. So we'll go on to here. So we can see here, again, each phospholipid here. Let's take phosphatidylcholine here, for instance. Phospholipids tend to have one tail, which is straight. This is called the carbon C1 attachment, which is straight, which is a saturated oil. So saturates have no double bonds, as we saw this morning. It's a straight one. They tend to have higher melting points. So they're solid at body temperature or room temperature to give the rigidity to cell membrane structures. The other C2 position, the second tail, is got a kink in it, or a bend, and every unsaturated bond in there is a kink. So if you've got one kink, like a match which is broken in the middle, this is a monounsaturated. And as we get further up, we get 2 and 3, and polyunsaturates, where some of the cells in the body could be 6 docosahexaenoic acid, or DHA, has 6 double bonds into it. So there's a lot of kinks in there, and this brings the melting point of the oil down. So these oils are liquid at room temperature and certainly at body temperature. So these particular fatty acids like EPA and DHA are liquid at room temperature, and they're rich in fish. And the reason they're rich in fish and oily in fish is to stop the fish from freezing when it's in the bottom of the North Sea. So when the cod comes down from the Arctic into the North Sea, it's pretty cold down there in the bottom of the North Sea. If we went down the bottom of the North Sea, we would go rigid. Do you know our melting point of the human body is now 30 degrees centigrade? It used to be 25, but we're now 30 degrees, which means that we go solid very much quicker. Okay? The fish, the EPA and DHA, have melting points of minus 13 and minus 15 degrees respective. So the EPA, DHA keeps the fish flexible even in the cold weather. It doesn't go rigid. Okay? Whereas if we went down there, we pretty quickly go solid. All right? Now this is quite frightening because it means that our melting point is increasing, which means our level of the oils in our body has changed, and we're getting more and more oils which are unsaturated but are performing like saturates. And these are called trans fats because they twist in the heating process and they straighten out so they don't have the kink in them anymore. So chemically they act like saturates with higher melting points. So it's not because we're eating more saturated fat, but we're eating more trans fat or heated vegetable oils and rancid oils and hydrogenated. Those are the three bad points about it. So we see here something that Sean and I were talking about at lunchtime is cholesterol is distributed between the leaflets. You know, between each one or two phospholipids is a molecule of cholesterol. And this gives the turgidity, it's called, to the cell membrane. Because if you didn't have enough cholesterol in here, see there, we would fall apart like an amoeba. We would just be one big blob on the ground. So we have to have our strength in our cells. And this is from cholesterol. This is good cholesterol. Okay? There's two types of cholesterol. There's good cholesterol and so-called bad cholesterol. And that's not really the high density or low density because both of those are necessary. The good cholesterol is here, but when it's oxidized, in other words, it goes rancid, it's called oxidized cholesterol. And oxidized cholesterol is the bad one. And this is fished out then by a high-density lipoprotein, which then carries it to the liver. And to carry it, it needs phosphatidylcholine. So it's piggybacked by phosphatidylcholine. And then that cholesterol, the oxidized cholesterol, is taken to the liver. It's then hydroxylated, or OH put on it, and then it's conjugated with two amino acids, conjugated with taurine and with glycine, and then that forms bile. So what happens is if you haven't got enough taurine or bile or glycine, you get an unconjugated bile, which is pretty nasty stuff. So when we talked about amino acids yesterday, the taurine, lack of taurine or lack of glycine leads to gastric problems here, reflux, regurgitation, and it's of a bile which is not conjugated properly, and it's foul stuff. It's really very caustic and irritating. Whereas if they take the taurine, they then conjugate properly the bile, and then you can eliminate the bile as an emulsifier of fats in the diet. Taurine and glycine, those are the two. So cholesterol is a major membrane constituent of human cells, being present in about the same molar amounts. In other words, there's almost as much cholesterol, and there should be, as phospholipids. So phospholipids, here's the two tails. See, one tail straight, and one's got a degree of kinks in it, and these kinks are the double bonds. The tails face inwards, so they're hydrophobic, so they don't like water going across, so the membrane can be somewhat selective. The head part here, the R part, might be choline, inositol, ethanolamine, etc. They're arranged in stacks, so the tails all face inwards in the membranes, and through these membranes come the proteins, the integral proteins, or receptor sites in there. These are the channels of how they allow substances like oxygen to cross by simple diffusion. So in other words, diffusion means it literally passes through the membrane. We may have transporter molecules to carry things across through the proteins, or by pumps, or the energy ones which require ATP. But what we're interested in today is simple diffusion, which means the greater quantity of oxygen on the outside will force it on into the inside. So key nutrients for making phospholipids are obviously the right types of oils, the choline, the serine, the inositols, etc., and the B3s. So hemoglobin saturation should be around in the region of 14 to 15. 14.5 will be the figure that you normally get as a blood test. If you go down to 10, you're generally considered to be anemic. So let's whip through those. Anemia can be something which we have a decrease in the red cell content, or we could have a decrease of the red and the white ones, which are aplastic anemia. Microcytic means small red cells. Small red cells is due to a lack of iron. And this is because we haven't got enough hemoglobin being produced, so the red cell doesn't swell up enough and can't contain the oxygen. So you get small cells. Hence the name microcytic anemia, which is iron deficient. Then you can get macrocytic anemia, which is because the cell isn't mature enough and they haven't got enough hemoglobin, and this is caused by B12 deficiency or folic acid. So these type of cells are macrocytic, which means they're bigger than normal. And this is interesting because this happens in the white cells as well as the red cells. We always think about B12 involved with red cells, but B12 is involved in the maturation of all cells in the body, including the red cell, including the white cells. You notice, because we find a lot of people are B12 deficient. Sometimes they can't convert the B12 into the adenylyl or the methyl. Sometimes people are just deficient in B12 because of not eating the right types of foods or absorbing it. Do you notice how much leukemia there is around? Isn't it common now, isn't it? People say, oh, I've got some chronic myeloid leukemia, lymphatic leukemia, as if they've got a cold almost. It's amazing. And you think, oh gosh. And they all respond to B12. And when on the blood test, they show you what happens with leukemia is they get more, but they get large white cells. Okay? They're immature, so they don't function properly. And therefore, they can't do their jobs. Check them for B12. It's amazing. They all seem to show it'll either be 12 hydroxycobalamin, the B12, or it'll be methyl, or sometimes more commonly adenosine. We may have hemolytic anemia, which means we're bleeding, which will obviously blood loss, heavy period, menstrual periods, etc., or fluid problems. But the ones we are really interested in at the moment is beginning to get the hemoglobin up. So iron deficiency, which is the center of the core of the heme molecule, may be deficient because of diet, not absorbing it properly, parasites which are grabbing it, in other words, something else is taking the iron before it gets into the body, and this is frequently parasites, they seem to love iron, or we're losing iron because of heavy menstrual or hemorrhages. So supplement with the different types of iron. We do iron chloride, iron sulfate, and iron phosphate. These certainly work well for the red, green, and blue body types. We've recently introduced iron citrate as well, which is a good form. So sometimes the citrate will work well, where the other three won't. But again, iron, like zinc, you have to test different types to be sure that the person is okay with iron. Hemoglobin and myoglobin. Now these are proteins. They contain heme. So this is again this word heme, which we see a cyclic tetrapyrrole consisting of 4 molecules of pyrrole, 1 atom of iron in the middle. So this is both for hemoglobin and for myoglobin. Now some years ago, my biochemist professor friend Igor Bondarenko in St. Petersburg, he said, Chris, he said, you should really study about heme, because he said it's very important to know all about heme. And I said, yes, Igor. And I had a look in Harper's Biochemistry and put it away again. And it took me again some years before I sort of went into it again and thought, this is interesting stuff. Because this word heme kept coming up in relationship to color and energy production inside the cell. So I started looking at the enzymes that are made of heme. Therefore, if you can't make heme correctly and you get the inability to synthesize it, you will not have enough of these enzymes. And these enzymes are rather important. So we've got catalase, which we met in detoxifying or reducing hydrogen peroxide. Myeloperoxidase, which is the one that goes on to make hypochlorite. Eosinophil peroxidase, which is the one in the eosinophils, which kill the parasites. Other peroxidases, which get rid of hydrogen peroxide. Inducible nitric oxide synthase to make nitric oxide. Cystathione synthase. This is the one that converts homocysteine into cystathione, which then goes on to make cysteine. So this, if we've got a defect here, we would end up with a high level of homocysteine because we're unable to synthesize it. Cytochrome P450. All the cytochrome P450 detoxification enzymes are heme dependent. They're all loaded with heme inside. Cytochrome for the energy production. That's the cytochrome Cs that we talked about earlier. And a very interesting one is sulfite oxidase. This is an enzyme that converts sulfite into sulfates, which is what happens when people drink foods or drinks with sulfites in them. You know, such as wine, which is sulfite is used as an antifungal to kill the yeast, you know. So wines and beers, if you get a nasty headache when you drink wine or beer, it may be because of sulfites build up because sulfite oxidase isn't working. And this is a heme-dependent enzyme. You can drink whiskey, gin, vodka, as much as you want, no headache. But one can of beer or one drink of wine and, oh, got a headache. And that's sulfites usually. Thyroid peroxidase, this is the one that adds the iodine to the tyrosine. This is important, of course, in thyroid function with people with low thyroids. Maybe nothing to do with what you think. So you load the person up and test them for tyrosine, you test them for iodine and DNA, and then you're going to show for B6. And you think, well, where does this come in? And the answer is it comes in because B6 is an important component of making heme. Cyclooxygenase 1 and 2. These are the big drugs against arthritis pains. These are the ones that stimulate the production of of prostaglandins 2 and leukotrienes B4, the pro-inflammatory chemicals cascade from arachidonic acid. So these are all heme dependent. Now, I put a lovely chart together. The one on the left is the same as the one on the right, except we look at a little bit of some of where the symptoms are on this one. Again, that laminate, is there other laminates out there somewhere? So Jill will show you this laminate. But the whole point is that from here, the making of heme starts here in the Krebs cycle. So it starts from alpha-ketoglutarate, which goes round to succinyl-CoA. So this is one of the components of the Krebs cycle. And with the addition of glycine, starts the whole process off. So succinyl-CoA to make energy in this Krebs cycle, and glycine starts the whole process off. And the end product is going to be heme B here, with then the addition of various proteins to make hemoglobin in this case. So we need to look at this in a little bit more detail. At the end of the day, if a person strengthens to heme, all you need to worry about is what nutrients are likely to eliminate this. We have the various markers at the various key stages for those who want to do that. Okay, and I like to do it, and you may want to do it, particularly if you've got people with porphyrin problems or pyrrole excesses. So here's our succinyl-CoA in the Krebs cycle. So we've got to have energy in order to make heme. And so we got glycine here and succinyl-CoA. Now, in this part, the propionic, isoleucine, methionine, and valine all go in and are burnt at succinyl-CoA. These are amino acids. And to get this to work, we need the active form of B12. So adenosylcobalamin is the coenzyme here. So this first pathway, ALA, which stands for alpha-aminolevulinase, or alpha-ALA, this enzyme here requires P5P, and it's very specific. It's pyridoxal 5-phosphate at this point here. The second part of the enzyme of the ALA synthase also needs P5P. So P5P, therefore, is a very, very important component, and adenosylcobalamin. So in this case, if we've got a person who strengthens to heme, we know there's a heme problem, a hemoglobin problem with them. Okay? So this person, we're getting in, they're hypoxic. Okay? They haven't strengthened to the phospholipid marker or the oils, but they do strengthen to heme, which means they're not getting hemoglobin ultimately to carry it. So your first marker will be ALA, alpha-levulinic acid, and if that strengthens, you then cross-check the person to adenosylcobalamin and P5P. Okay? Two of the biggest coenzymes that the body uses, okay? Very common ones. So adenosylcobalamin to start the process here off to burn these amino acids, and P5P. So if we follow this along, our next substance that we make is PBG. PBG stands for porphyrobilinogen. PBG is the first pyrrole ring. We see a ring forming now. This is called a pyrrole ring. So we've got two molecules of ALA, an ALA dehydrase enzyme here, which appears to be zinc and magnesium dependent. So now we've got B12, B6, magnesium, and zinc. Gosh, these are all the things that everybody buys, aren't they? For one reason or another. You guys buy more magnesium and zinc and P5P than anything else. So does everybody else all over the world. Which would indicate, if you know where your body uses these, is most people have pyrrole problems. They have heme, they're not producing enough heme. So if we can't get this far and the person strengthens to PBG, well, they'll weaken to ALA. All right, so the same basic rules of functional biochemistry, which means this person is probably zinc or magnesium deficient. Okay. So now we've got to PBG. Here's PBG, as we follow it down, goes to hydroxymethylbilane is the next one. And at that point here, this enzyme here gives off 4 molecules of ammonia. And we know we've got to burn ammonia in the in the urea cycle, and this needs biotin. So these people, if there's a blockage here, get a build-up of ammonia, which drives them crazy. And these people are called pyroureas because they get a build-up of PBG. And this then shunts itself down into these odd metabolites, hydroxyhemopyrrole, used to be called cryptopyrrole, in this particular direction, which have got the blame for causing all sorts of psychological problems and behavior problems, particularly in children. But I think a lot of it is the fact they're getting a build-up of ammonia in their brains. So these kids need, or people need, biotin. So now we've got B12, B6, magnesium, zinc, and biotin. So we've got B12 in there again. So let's follow that on now. So hydroxymethylbilane then goes on to the first real porphyrin, which is called Europorphyrin. So this part here of the conversion here needs calcium and magnesium, but it's inhibited by copper and mercury and cadmium. So these are poisonous substances that we know. So if we have these poisonous substances inhibit here, we may get a build-up of PBG, which again makes people a little bit psychologically disturbed, let's say. Okay, so now we make Europorphyrin. So Europorphyrin, UPG, is then decarboxylated, and all enzymes that decarboxylate need B6, or pyridoxal 5-phosphate. So this converts to coproporphyrinogen, or CPG. Now both these are interesting because if we don't convert here or here, if we've got a B6 deficiency, or this enzyme is inhibited, in the presence of light, Europorphyrinogen will go along to europorphyrin here, which generates free radicals. So this light here, if it's exposed to light, these people will generate superoxide from oxygen. So this is damaging because we know superoxide will then go on to make hydrogen peroxide, hydroxyl radical, etc. Now, if you can imagine this occurring in your eyes, because the place that where you see light most, of course, and receive light is your eyes. So if you are sensitive to light, what you will find is that you will develop high levels of superoxide behind the eye. And if you put superoxide in the eye, it converts to hydrogen peroxide. And so you can imagine hydrogen peroxide in the macula of your eye, what it will do. Okay? You get macular degeneration. So now you begin to see, where macular degeneration comes from. Okay, macular degeneration is degeneration of the macula of the eye. And nothing will make you lose your vision quicker than hydrogen peroxide in the back of your eye. Okay? It's not the sort of thing you would normally do. So these people don't like light. Okay? So they squint, they close their eyes, or they wear sunglasses all the time. And this is the story of King George III. So King George III was known to make rash, stupid decisions, like sending the troops into America when he could have calmed down the local people who were there. And we may still have had America as part of the empire. May have, okay? And they would have had a special relationship with us rather than the other way around. Okay. So he made illogical decisions in there. But they noticed because his love was outdoors, but they called him Farmer George. His love was outdoors, that when he was outdoors, he became quite insane. And when he was indoors in Windsor Castle, he made more sensible decisions. But this was observed, and they didn't know why. For 200 years, they basically never discovered. And then somebody said, he's got porphyria. because he couldn't take the light. When he was out there, he went completely sort of insane. The poor guy, if you watch the film The Madness of King George, it's a very interesting, but it's a little bit of literary development in there, because it's not strictly true. The psychologist who was supposed to cure him in a pretty rough way, there was no evidence that that guy ever existed. What they do know is they did observe that he was better when he was indoors, and they basically kept him indoors. But he slowly became more insane, and the last 20 years of his life, from 1800 to 1820, he was totally insane and in a lot of pain, and really an invalid. He'd gone blind and everything. And when they did a study on his body after some time, they did find it was riddled with arsenic. So they don't know, of course, whether arsenic was inhibiting here, like mercury and things, and building up those porphyrins, or whether he was being actively poisoned by somebody who wanted to take the throne over. We won't mention any names who that was. Okay. So anyway, the point was that it's known that these high levels of these intermediate substances, Europorphyrin, coproporphyrin, and protoporphyrin, as we go down, will shunt upwards, and in the presence of light will convert to porphyrins, which cause porphyrias. And the first observation they made is these are highly brightly coloured purple substances. In the presence of light, they actually convert. And what they observed with George is his urine was purple. And directly that was spotted by the doctors. They should have known what it was, you know. But they seemed, if you watch the film, more interested in his feces than his purple urine. I would have been more interested in the purple urine, which was more applicable, that there was something desperately wrong. So the purple urine was the giveaway. So when it went exposed to light, it goes purple, you see. It doesn't always do that, because sometimes you can see. But the fascinating thing here is when you read this in Harper's Biochemistry, he actually explains here that it's not just any old light, it's 400 nanometers. 400 nanometers is the wavelength that does the conversion of the porphyrinogen into the porphyrin. And I think we've got that somewhere, Jill, there, haven't we? Is the 400. So if we could have the 400 out. Now, could I have you back at this stage? Now, 400 is, as we learnt yesterday, when we were studying colours and things, is really the first part of the violet end of the spectrum. So we're going from the blue indigo, and I count 400, 389, 395, 390, 385 as the violet end of the spectrum. So what we want here is we're going to put the 400 over our eyes, and because I think you've got a heme problem. So you look through that, and we pull up, and she goes, wait. Now I'm going to put my money on the fact she's got porphyrin. She's have difficulty making heme. The reason I know that is because the enzyme that she was deficient in the mitochondria, cytochrome C, is a heme-dependent enzyme. So I think she's got a heme problem. So let's go back now and have a look at the heme pathway. So what we're going to do here is we can go back to any weakness. We could use the blue here, or we could use ADP. Let's just use the blue. No, let's use the ADP, because that's a nice little marker there, because it feeds us into ADP. So it keeps us in weakness related, and we're talking about energy. Okay. Now, if you can give me ALA, alpha-levulinic acid. So this is the first in the pathway of making porphyrins. Okay, so she doesn't strengthen that. Now we give me PBG. This is the first pyrrole. And then what the body does is it puts 4 pyrroles together. And this is called the porphyrin. So we want europorphyrin first. Okay, so this is the first one. And then we go now to coproporphyrin. Okay, now, perfect, because now if we go back to europorphyrin decarboxylates to copro, which means europorphyrin will weaken her because she's got a relative excess. Could we have the chart back on, Gary? So we got you back dead on the right pathway here. So what we've got is we've made our europorphinogen from PBG. So we don't strengthen to europorphinogen, but we do strengthen to coproporphinogen, and we weaken to europorphinogen, which means our problem is here. Okay? Simple, really. Okay? And what is the mechanism here is a decarboxylase enzyme, which means it's P5P, okay? Pyridoxal 5-phosphate. Simple, it's a decarboxylating enzyme. This is a P5P. So her result of having a deficiency of P5P is that she's got to build up a europorphinogen, which in the presence of light will create superoxide. And she doesn't want that, really, because how do I know that? Because we can have superoxide as the test. So we're going to put superoxide and NADPH on. These are the markers for superoxide. And she's strong to that. And now let's try hydrogen peroxide and see if it's gone to the next stage. So she's fine. But let's put her in the light at 400, which would be now if she went outdoors, okay? So this 400 level there, different matter altogether, okay? So now she goes weak to the light, and that's really bad because if she's exposed to the light without any protection, she'll produce superoxide in the back of her eye, okay? And in other locations. So sunbathing at the moment is not for you, okay? What? Made her feel really bad the other day. Well, it can do more than that. It can damage your eyes if you don't wear, the right glasses and things. But what Harper says is it's the treatment, not the cure for this, is beta-carotene. So I went to beta-carotene. So the Master Nutrition box there. So you should see, let's try beta-carotene. So we're following the book entirely of the Masters. So beta-carotene doesn't do anything. Beta-carotene is a carotenoid, nice orangey substance. So give me another carotenoid. Lycopene, maybe? Lycopene is a red one. Okay, so it's not lycopene. Give me astaxanthin. Everybody talks about astaxanthin being a sort of red, orange, pinky colour one from salmon. So those are no good. Now give me, is there a mixed carotenoid in there? I think so. No, in a minute. Is it? Okay, so let's go for zeaxanthin now. So zeaxanthin is an orange one. Zeaxanthin, again, is rich in kale. It's the orange part, so it's produced some orange marigolds. And it particularly protects the macula, or the cone cells. So that does nothing. It now give me lutein. Lutein is more the yellow substance. And we see that lutein strengthens her very nicely. Now, we do two products of lutein. We can measure her with just lutein itself, which is the yellow compound which is rich in kale, or the mixture, the smart lutein, which is a mixture of kale and the lutein from the marigolds. Okay, so we know that. Have we got any lutein here? She doesn't need the zeaxanthin. The zeaxanthin isn't necessary for her, so probably the smart lutein would be the better product for you. Okay? Now, lutein is yellow. What does this mean? Okay. Why does yellow help her? Because it's the complementary color to the blue end of the spectrum. All right? So it's acting as a blotting paper. Okay? So anything which is yellow is good for her. So a yellow color. So this will be the color that she needs for her sunglasses. Okay? Will be on the yellow end of the spectrum. Okay? So what we're going to do is measure, when she's got this substance will get into not just her eyes, but it will get into your skin, and you'll be able to sunbathe fine. Okay? So this is not a cure for her problem. This is going to be something that she can take to protect her from the effect of 400 or the violet end of the spectrum. So she goes to 3. We've had people up to 15 capsules, so she's not that bad, right? But it's bad enough to say, well, at your age, you need to take some protection in. But her real issue, of course, is not so much of taking the lutein, which will help her, is to be able to actually get rid of this europorphinogen. So what we want to do now is we want to put the europorphinogen back on. Oh, have I got it? Sorry. Yeah. So Europorphyrin weakens. Now bring out the P5P. So P5P, pyridoxal 5-phosphate, is the active form of B6. So we do this in two forms. Let's do the capsule. So the capsule is a powder. It has a little bit of rice bran in it, and she strengthens very nicely to that one. Let's try the liquid. Sometimes, and I've only noticed this with P5P, sometimes people work better with the liquid, and sometimes they work better with the capsule. Most people luckily work well with both, but sometimes one will always work better. See, in her case, the liquid doesn't do anything. So giving her a liquid won't be as effective, obviously, anywhere as a capsule. So do we have a P5P capsule around? So while we're getting that, we'll just put that on. All right, so what we've got is the Europorphyrin as our marker, and P5P is the remedy. While we're doing this, let's see now and see if that is the case. So we'll put the P5P against the 400 acetate, which works a trait. So her real problem is probably going to be P5P deficiency. Now, before we do that dose, let's try pyridoxine. All right, pyridoxine is B6, isn't it? Plain B6. So let's use that as a marker. And what we'll see is whether she can actually convert B6 into pyridoxal 5-phosphate. And the answer is no. Do you see this? All right. That means she's got a polymorphism or a SNP, single nucleotide acid. She's unable to make enough pyridoxal 5-phosphate from pyridoxine. So she is not deficient in pyridoxine. Okay, she's not deficient in B6 in her diet. She just can't get it to work for herself. Okay, so she needs to take the pyridoxal 5-phosphate to build the levels up. Now this may be a certain dose, which we'll work out in a moment. And we keep her on that dose for 2 or 4 weeks. And then what should happen is it will halve and halve and halve. But you'll get to the point when she comes in and it doesn't show anymore. And 2 weeks later, she'll ring you up and say, I'm as bad as ever. All my symptoms have come back because we only store it for about 2 weeks. Okay? If you're not making enough, you're not then getting it back in through your diet. And you'll be all right. And I've done this so many times with P5P, and all the symptoms come back. Okay? So if they show the P5P, you want to drop it down and then perhaps do a little maintenance of a few capsules a week, even just to keep the level up. So what we're going to do is we're going to try now the P5P. So we'll do the capsules, as this is the most effective way. So we'll put 1 capsule on. These are 25 milligrams. We know that the recommended daily allowance of B6 is 1.8 milligrams. So she's going to 25. That's quite a large amount. She's going to 50 milligrams with 2 capsules. She's going to 75. She focuses now on 75 milligrams. Remember, the RDA is 1.8. So you can see how bad she is. She needs 75 or so milligrams. Okay, so she's really down there because she's not converting. Okay, so if she was to say, well, I take my 1.8 milligrams, I eat my liver and my rice brans and things every day, but she can't convert it. So we'll find that after a few weeks, you'll show to 2 and then to 1, and then maybe 1 every 2 or 3 days. And then if you give it up, you'll find 2 weeks later, bang, it'll come back. So there's a polymorphism in there, which usually means it's an inability for the gene somewhere in you to be read properly. And that gene is for the kinase or the oxidase enzyme to convert pyridoxine into pyridoxine. A lot of the population have it, don't worry. But this is why you need the P5P and not just B6. So try not to think about that you're deficient in B6. You're deficient in being able to get it to work for you. All right? Now, is that the answer to all the problems? Let's go back to the ADP, which was our original energy marker with her. I don't think I've got it, have I? I may have it. Yeah, I got it. So ADP was the original marker that we came in with here. Now we'll put the 3 P5Ps on. So how do we know whether that's enough of a substance? So we've got 2 things. What we can do is we can take the ADP on and off. This was our reference marker. So we're just putting on the ADP a few times. And if it goes into weakness, we know there's something else. But she doesn't. She stays strong. When should she take it? let's try the 3 meal times, because normally with B6 you'd get it from your food. So we go circulation sex for the evening meal. Now, let's go now breakfast time at stomach time. Yes. And let's go small intestine at lunchtime. Now, so it's P5P for breakfast, okay? You can have ordinary breakfast as well. Does she need the lutein? I would use the lutein as well. I'd eat kale in your diet, one of your 5 leafy green vegetables, to get the lutein in naturally. And I would, for a short while, at least over the summer, while the intensity of the ultraviolet is high, this time they use lutein as well. And remember this all your life. All right, don't forget this. Because as you get to 60 and 70, the effect of light starts to age the eyes. And once the macula's gone, you know, at the moment, maybe in 60 years' time, they might know the answers to this. But at the moment, if you lose those cells in the back of the eye, you don't regain them. Stem cells would be the only thing that we know of vaguely, but it's better to protect them. So lutein and zeaxanthin, kale in the diet. Do this till, say, the equinox, till 21st of September. Take your 3 P5P for a few weeks, and then start to slowly get it reduced, and get somebody to monitor you, you know, to do the figures as you go along, right? To say once a month or once every 2 or 3 months, go and see somebody who can workshop with you.